the competition aspect of the computational challenge. So I hope that all of you have been thinking about doing something, but in fact, more to the point, doing something, trying some small element of what's been Dr. French has taught through the past few weeks. This is the crunch time where you think, well, am I going to participate? You should try. You should endeavor to sort of develop your skills and have a go. You don't need to do something grand. Don't get carried away, but do something simple. And then you might be encouraged to develop it because you find it interesting. So that's the key issue. We're going to be putting up some more details on the BPhO website shortly. We haven't got access to it at the moment. We seem to be locked out of the editor, but that will come. So Dr. French is going to talk about the general idea, and I think he's going to do one or two of last year's submissions, but don't feel intimidated by them. Some of them are extremely good. This is at the very, very top end. And what you want to do is be realistic, do something, and then if you're satisfied with that, that's great. If you think this is really exciting, I'd like to do more, then that's fine. But don't just sort of take a look at something extremely well concocted and then say, oh, I can't do anything like that. We're not expecting you to. What we want is to encourage you to develop your skills, and that's important. Okay, right, there we go.
Okay, thank you very much, Roman. Good evening, everybody. So this is going to be the last session of the 2023 Computational Physics Challenge. If you've been coming to the last sort of 10 sessions, fantastic. If this is completely new, well, welcome indeed. So I'm just going to go and share my screen and let's sort of have a look at this year's challenge. So what I'm going to do is sort of talk to you about the challenge specifically, which this year is on solar system orbits. Okay, so and then also give you some of the generics of how to go about the challenge, and we'll talk about that for maybe 20 minutes or so. Please put some questions in the Q&A. I'm not going to be talking for a great deal today. My voice is a little bit scarred from my recent trip to the mountains. So please ask lots of questions and about how this is going to go about. So let's introduce the challenge, and sort of as we go, what specifically are you going to do? So for a start, so this is all about the solar system, and you've got between now and let's just say middle of August. I think we'll put an exact sort of deadline, but it'll be something like that, to follow a series of tasks, which we've graded gold, silver, and bronze, and see how much you can do. And we've got some ideas for extensions as well. I'll show you where to download this presentation shortly. So, all right, lots of text here. So I'll just sort of walk you through it. You best to sort of zoom in on this. But basically, we've got, you can get a gold, silver, or bronze, all right, depending on the kind of tasks that you achieve. So we've got plenty of bronze level ones. So for example, if you're very new to spreadsheets and you're not quite sort of sure about programming yet, it's eminently possible to get some bronze things. To get the silver, we're looking for a bit of basic programming and all the spreadsheet parts complete. Whereas to get the gold, we're looking for pretty much everything. Quite a lot of computer programming, maybe lots of extension work as well. And most people who got gold did all sorts of things last year. Some people wrote apps, some people wrote websites. We had little papers as well. So particularly if you want to have a crack at the top 5, and we'll show you some of the videos for that a bit shortly. And they're going to be rewarded at the Royal Society next week with lots of the other BPhO competition winners. So ultimately, you're going to be working individually or in pairs. And the idea is to produce a 2-minute YouTube video which describes your entry and what you've done. Okay. So there we go. Some information about how you might want to do a screencast, but we'll leave that up to you. I quite like something called Screencastify, which is a Chrome add-on, but you may have your own systems for doing this kind of stuff. All right. So basically, I'll sort of walk you through the kind of presentation, really. So we've got some theory of Newton's law of gravitation. and Kepler's laws. All right, so there's some maths here. So all the information inside the presentation should be all you need. So these are the sort of elliptical orbits and the forces, etc. These are Kepler's laws of motion. So a lot of you will be familiar with this. But we have, you know, elliptical orbits. The areas swept out in equal times are the same. And the period squared goes as the orbital radius, or the semi-major axis cubed. All right, so well, these are all the sort of basic mathematics of orbital motion. So what are we asking you to do? Well, if we start simple with Kepler's third law, and you write this in years for periods and astronomical units. So what we do is we write down Kepler's law, and we say that the masses of the planets are very small compared to the masses of the sun. So we can say p squared, the period squared, goes as essentially the radius cubed. So let's assume we've got circular orbits. And then if we work out what we do for Earth, so that's a year squared is this lot times 1 astronomical unit cubed. That's the average distance between the Earth and the sun. And we divide those two expressions. You find all the sort of 4 pi squareds disappear. And so the simplest way of writing Kepler 3 for the solar system is the period in years is the semi-major axis, or the radius in astronomical units, to the power of 1.5. So there we go. We've now got a relationship which we can test. And so your first thing to do is to basically, here we are, plot this graph. So to verify that Kepler's laws works, and I'll give you all the data. This is the sort of data table for the solar system. So in this case, we've got things like the distance from the sun and the orbital period. I've also given you things like the rotational period as well, and that kind of stuff. But it's those two things which we need. So the first thing to do, we're putting that into a spreadsheet and confirming that Kepler's law works. And you can do lines of best fit. You might wish to program that up yourself if you're doing that in Python. It turns out it's a very, very good line of best fit. Okay. You might also want to plot this graph, which is the orbital period versus the semi-major axis. So this is all about clarity, but essentially you're building spreadsheets or computer models to plot these things. So that's the very first challenge, and that'll be a kind of a nice bronze level. Okay, so and now sort of perhaps a little bit harder. You could do this. This could be bronze, but it could probably more likely to be silver. Is that, you know, you might want to use a computer program to actually plot the elliptical orbits. All right, so well, the mathematics are here, and how do we convert range, all right, and bearing into x and y? Well, we can use some trigonometry. So r cos theta is the x coordinate, and r sine theta is the y coordinate. So we can use that. We can define, you know, theta going from 0 to 2 pi radians. We can work out how r varies with angle, which will give us your ellipse here. And we can then use that to plot our orbits. So there we go. These are the inner planets, and these are the sort of outer planets. Okay, and there's a very good video called The Solar System to Scale, which was done by an American team. They went, I think, to the Black Rock Desert with a car to map out these things. So you can't see the planets on this scale at all. All right, the radii are to their dots. So I think they use sort of various LEDs, you know, and the distance between the planets are of the order of kilometers. So you can make this yourself, which would be quite nice. And then the sort of a scale, which is definitely kind of in the programming territory now. So it'd be difficult to do this in Excel. It's so animated. All right, so we can work out, if we know the period, the angle in t seconds is 2 pi t over the period. Okay, so it's you know, how many periods times 2 pi radians is the angle. So we can then use that to work out the sort of an animation of the planets. Okay, so you can get that sorted out. And maybe if you take Jupiter to take 1 second, that's quite a good time scale. So there we go. That's the sort of getting started. And then you might want to make it 3-dimensional. Okay, so a bit of 3D graphics. So things like MATLAB and Python. Now I'm not sure about Matplotlib if that does it in 3D. So you might need to sort of think about finding some tools or libraries that will allow you to plot in 3D. But MATLAB certainly does it. And we need to sort of rotate the coordinate system. So there's a little recipe here for how to do this. All right, and it doesn't really look much for the inner planets, but for the outer planets, you'll see the dwarf planet Pluto in away from the plane of ecliptic. So its ellipse is tilted compared to the others. all right, which is quite nice to watch. Here's some more data points for all the planets. And now we're starting to get a bit harder. So bit of maths here. I'll let you look at that at your leisure. But basically what we can do is we can use Kepler's second law. So the rate of area swept is a constant, all right, as we go around, and it turns out it's given by this. We can use that to work out the time versus the angle, all right, because the area itself is, well, is basically given by this, a half, r squared d theta, all right, is this lot. So essentially what we can do is we can, so dA r squared d theta, that's that little sector there, all right. Excuse me. There's a half that should be in there. I'm just having a look at this, but anyway. So basically what we can do is we can work that through, and we can devise an integral expression for our time in terms of angle. And unfortunately, this isn't a kind of integral that you can do that you will have met at your A levels. It's called an elliptic integral. But what we can do is use a numerical method for solving these kind of things. So what we can do is we can use something called the trapezium rule, or even better, Simpson's rule, which is where you're fitting quadratics to these little things. So what you might want to do first is code this up in a programming language. So you can sort of have any function you like, and you can say what's the area under it. That's quite a nice little thing to do to find the area under curves. And I've done this in MATLAB, and I've made it sort of visual, a kind of visual calculator. And it turns out there's a nice recipe for this. You sort of take, if you imagine you've got a number of y values separated by sort of a fixed x distance, what you do is you add the first and the last one, and 4 times the odd numbers and twice the even numbers. That gives you a good approximation of your area under it. That's using Simpson's rule. That's quite nice. So that's something that some of you may not have come across before, but it basically means we can find out the area under this curve. So basically, yeah, so you do a kind of cumulative sum, and you can then work out the polar angle versus time. And what you'll find is for these sort of elliptical orbits, Pluto's is a pretty good one to pick. All right, they're not the same as the circular orbit. They sort of wiggle around a bit. All right, so you can use that to make quite an accurate determination of time versus angle. And then we can use that. There's a sort of example of what I would do in MATLAB, for example. You can sort of use a different code for whatever language of your choice. And then we can work out time versus angle. Now that's quite useful. So we're kind of getting into the silver gold stage now. And then the really pretty stuff is what happens at the end. So challenge number 6 is to make a solar system spirograph. So what you do is you pick a pair of planets. I suppose you could pick more than 2 if you want, but pairs kind of work for this. So this is Venus and Earth. So Venus is the sort of yellow, sort of puce-coloured orbit, and blue is the Earth one. And what you do is you find out where you have a time scale. All right, so we use our function to work out what angle we get for a given time, and hence the position of our orbits. And then what we do is we draw a line between them, okay? And we just keep doing that. So I reckon maybe every month or something like this. And what happens is we end up making this wonderful sort of stitch pattern. With Venus being a sort of 5-point star. So there's a kind of, gives you a visual sort of representation of the kind of ratios of the orbits. So Jupiter, Saturn, that's quite interesting. But in order to make this work, if we're using the proper elliptical orbits, we need to do our Simpson's rule. We need to work out the time, so the angle versus time. Of course, you could make an approximation and you could assume the orbits are circular, and you'll get something that looks a bit like this, but not quite as good. All right. So perhaps you could do that, a simple one first, and then try and work it out properly. So here's Mercury, Earth. Here's Uranus, Neptune. Neptune, Pluto. That's quite interesting. You certainly see this sort of strange elliptical effects. They're sort of off center. Venus, Mars is quite good. And there we are. So I hope that's quite interesting. And the last challenge, at least of the sort of non-extension stuff, is to go back to Ptolemy. So Ptolemy, as you may know, about 2,000 years ago, sort of proposed this sort of idea that the Earth was the center of the universe and all the planets sort of rotated around the Earth. Well, you know, relativity and all of that, that's a perfectly valid, the Earth could be the center of the universe. You know, there isn't a sort of, you know, when we know about cosmology, there isn't really a center anywhere. However, this does mean the motions of the planets and indeed the sun is complicated, because it's a much better model to have the Earth orbiting around the sun being fixed. But we don't have to bother with that. So this is all about trying to sort of use our orbital models and then have something else being the center other than the sun. Okay, so everything has to orbit around each other. Okay, so here we go. So this is what the Ptolemaic system would look like. That's the Earth at the center, not moving. So the sun now is a 1 astronomical unit circle, and you can see all the others. You've got Mars with its little epicycles. All right, you've got Venus, etc. All right, so this is quite fun. So once you've got a model of all the orbits, you can kind of subtract one from the other, and you can have it relative to any of the others. Okay, so you kind of don't want to go straight to this project. You want to go through the challenge first. But if you get to the end, you get a way of saying, okay, let's say Venus at 3 months' time, where's Venus going to be relative to the sun, for example? Do the same for the Earth, and then you can subtract it and work out relative to the Earth where Venus is. So this is quite nice. So this is the Ptolemaic. Let's just say we were Saturn was our home planet. We can do that instead. And there we go. And what extension opportunities could we have? Well, you could maybe look at some other systems with exoplanets. All right, so there's lots of data now. So in other words, systems which have different masses to our sun. So it's going to be scaling, but it will be a bit different. Okay, you might have some binary systems as well. That might make things very interesting. Okay, so and there was one of our online seminars which talked about how you can look at the orbits of those. So that might be a bit of a departure to work out that, because of course, we don't have Kepler's laws now, because we've got maybe 2 suns. But that might be an interesting extension once you've done the other things. You could do everything we've done so far in a GUI, like a smartphone app. That would be really nice. That will particularly impress the judges. And also a nice thing to do is to write up a little paper. You could put all these ideas into your own words, add your own spin on things. I go for about 10 sides of A4. Think about a kind of small paper that you might want to publish. A lot of people use things like LaTeX. So this is the sort of language of science. There's lots of links here, including my book, which was all written the same kind of thing. So there's loads of things you can do, but I think probably look at exoplanets, write some sort of GUI. All right, if you're really good with computer programming, Python or JavaScript or something like that, and maybe write a little paper. Okay, some of the top entries last year did most, if not all, of those things. All right, but as Dr. Hughes mentioned at the beginning, don't be put off by that. If you are at the bronze level, that's absolutely fine. Get stuck in and see how far you get. Okay, so there we go. That is a little sort of tour of what we're doing. I'll just quickly show you where to find it. So if we go to my website, and we'll go to the BPhO website first. So there we go, bpho.org.uk. If you search for computational challenge, there will be some details here. I think this is one for last year. I think if you scroll down, there might be something for, I think it's this one. Anyway, more information will appear here. But you can also download it from my website too. And I'll just put that in the chat. There we go. There we are. So that one, and I'll give you the BPhO one too. Okay, if you want to copy that out of the chat. So you can have access all the sort of talks and the materials for the courses we've done this year. And you can see last year's challenge, and there'll be a challenge for this year. I can't remember if I've got a YouTube link yet. Not yet. So I might make a little video of this just to sort of give you a quick briefing. And if that goes online, that will be the little red triangle. But if you click on this, you'll get a zip file with the challenge for this year. So pretty much what I've just shown you. So this thing here, this presentation. Okay, so basically that's it. All you need to do is sign up on the BPhO website, download the materials. There will also be a little briefing document as well, if you like sort of keep things nice and tight. This has all the sort of 7 tasks in summary form, plus some ideas about extensions. And then you can use that to work things through. There we go. So over to you. Do you have any questions?
There's lots in the Q&A.
Right, fantastic. Okay, wow, loads. Okay, let's go to the top. Where did you get the data from? Okay, okay, so Martin, so that I think this is a combination of NASA and Wikipedia. So as I say, there's you might sort of particularly where you start the planets from. There's something called an ephemeris rather, which is where the planets are now. So there's an interesting sort of where do you start? So when time starts from 0, you might maybe have all the planets aligned, for example. But you know, if you actually want to go onto the NASA website and use where the planets are now, that might be quite cool as well as an extension. Right, for the animations, is matplotlib pyplot usable for animations multiple points? Ooh, not sure. As I say, I'm not a massive expert with these because I tend to use MATLAB, but that's worth persevering for. Certainly Matplotlib will do 2D, not sure about the animations. There's something called Pygame, which might be easier, but that might be something you want to Google. We'll be able to access this recording. Yes, absolutely. Does Challenge 7 need to be 3D? So Challenge 7 was the sort of Ptolemaic stuff. To be honest, I've made it 2D really. You could make it 3D. You can sort of see here. That looks quite nice. But to be honest, only really that's important for Pluto. So I think from sort of a visual perspective, it looks much better in 2D actually. Can we do all the code in Excel spreadsheet for gold? Oh, I think that'll be tricky for gold actually. So I think we've said to get gold, you really need to get stuck in for some computer programming. But you know, if you were really, really good with Excel, you might be able to do something, get towards the silver, I think. But this is an incentive to learn a bit of computer programming, I think. Could we go around submitting a paper to be judged? Do we have to record the scrolling through it? Right. Okay, yeah. So we've got this interesting constraint about the 2-minute YouTube video. And we just want to sort of see some evidence that you've done the work. I'll show you it a bit later. You know, we're not going to be marking your paper, I'm afraid. This is much more about you just, you know, getting involved and having something which looks reasonable. We know we're going to be looking at probably 100 of these, so it'll be fairly obvious. You'll all be solving the same problem. It's more to case to show what you've done. We'll show you some videos in a minute. All right, on the competition briefing document, the hyperlinks don't work. Is there another way to access them? Oh, that's very interesting. Right, that should be the case. I'm going to go and check that now, actually. So 2023, that should be the PDF. So I'm just loading that up. So let's have a look. That should challenge presentation document. Yep, so that's that goes to the websites. So I think they do work. I think we'll, you know, if there are some problems, we will update a few things. Programming resources. So that should take you. Yeah, that should take you to my website. So they work on my computer. Sorry if they don't on yours. That you might just want to load it into a different Acrobat thing. How do I sign up to the challenge? Is there any form I need to fill in? Yes. If you go onto the BPhO website, that's the place to do that. What would the final conclusion of the paper look like? Yeah, so yeah, you're absolutely right. It's more of a walkthrough of the challenge. You might say, okay, I'm going to model, I'm going to use computer program to model the orbits of the solar system, or perhaps some exoplanets as an extension. And I'm going to my final point of call is I'm going to look at a revisit of Ptolemy's model. So I'm going to work out a model for the motion of the planets with a view to setting a different planet being the center, the fixed point. That might be your sort of starting your sort of progression through your project. Do you have any gold examples? Yes, we'll show you those soon. Previous year's entries. Well, we're going to release, I think, the top 5 videos. You can access my presentation. If you actually want to get the entries for it, have a look at the videos which we'll put up soon. Do we need to sign up now? I would sign up fairly soon, but basically you've got until August to do it. And can you show the form to sign up exactly on the website? I think I will leave that to Hughes to show you where that's going to be.
It will be on the page. Unfortunately, we happen to be locked out of the web page editor at the moment, so we can't fix it until the weekend.
I see. And is this gratis, or is there a cost involved with this, Mr. Hughes?
No, it's all free.
Fantastic! It's free. Hooray! Excellent. There we go. You can buy Science by Sim if you really want to part with some money, but but yes, the project is free. Excellent. So let's go and show some of these videos. Right, am I still sharing my screen? I am. Right, so if I go into the chat, we have some from last year. So let's find, let's have a look. We'll go for Valeria Badham and Victoria Badham, UK. They did theirs in Python. So I'm not sure how the sound is going to come across here, but we'll give it a go. So I'm just going to put that into YouTube. Right, and I'll make that nice and big.
Hello, BPhO team, and thank you very much for taking the time to watch our presentation. I'm Nicholas Gregory, and here with Jamie Whiting, we will be showing you our entry for the Computational Physics Challenge 2022. We completed all 3 tasks and embedded them into a progressive web application, something you can run on any modern browser or install into your phone, tablet, or computer.
Now, can I just check, is that coming across okay?
Yes.
Right, excellent.
So let's dive into our application. It uses React with TypeScript on the front end, and the actual computations run using WebAssembly on the client side. The first task is set out here, a simple graph of temperature against altitude in the ISA. On each task, we've added brief explanations, such as this one, where we note our calculations and the data used. In task 2, we've tried to allow users the utmost flexibility in determining the lapse rate, pressure, and temperature for the calculations via these sliders. This then produces the color-coded graph below, showing each stage of the atmosphere and calculating pressure. Here you can see the TypeScript code we implemented to evaluate the mass expressions. Task 3 required the most work. We produced 5 plots of pressure, temperature, dew point, lapse rate, and boiling point for a given humidity. These can be calculated using either Euler's method or Runge-Kutta for better speed, and it's really where WebAssembly shines in its computational power. It's buttery smooth. A simple implementation to solve the task is shown here, yet we chose a more developed method with greater efficiency. Finally, you can compare planet data as well as the extension activities. We created a technical report to show how we implemented these tasks and explain some of the choices we made whilst doing so. We chose to use Rust and WebAssembly because it's far faster and more efficient than running calculations in JavaScript or Python. Due to the unacceptable overhead from the graphing model we used, we wrote an implementation of the Raman-Douglas Ecker algorithm in our WebAssembly module to achieve perfectly smooth performance on the client without any noticeable degradation in graph quality. Thank you for giving us this opportunity. We hope you enjoyed our project. Please visit bpho.kim, the link's in the description.
Right. So that was probably the most advanced entry we had. As you can say, these guys had a lot of skills in IT. They made a website. So their last year's project was all about the standard atmosphere and plotting pressure versus altitude and that kind of thing. So they really went to town on it. So that's kind of perhaps one of the ultimate extreme. They even wrote a little paper too. Let's see if I can find some of the others. So let's go for this one. I hope I've got the right one here. Here we go. It's getting there.
So this is a GUI made using Python with management. So starting off with the Earth, we have our temperature and pressure graphs made from the Excel spreadsheets, and then the numerical method-based graphs, as well as the sliders for temperature, pressure, and humidity. The red arrows are the average temperature and pressure for Earth. And it's interesting to see how lots of the graphs break down at extreme temperature and pressures, which aren't entirely physical, like this one. And this is how it looks. And just a couple of the other ones. These white dots are portals into even more graphs. So this is a size comparison between the Sun, Earth, Venus, and Mars. And we didn't include the corona outer layer of the Sun's atmosphere because it's too large to fit on the screen. These are side-by-side scale diagrams of Earth, Venus, and Mars atmospheres up to the upper limit of the thermosphere, but not including the exosphere. For our ISA model of Venus, we fitted lapse rates to data from probes such as Venera and Pioneer Venus. We later found that our model fitted very closely to the Venus International Reference Atmosphere model, with the main deviation between 40 and 60 kilometers where there are sulfuric acid clouds. That's for latitudes between 0 and 30 degrees. For Mars, the data was very not smooth, so we based our lapse rates entirely off of 2 Martian atmospheric models by NASA, with the green behind Mars brown model. And the final white star is a graph showing cloud formations at altitude for the different planets.
Yeah, so this was great. So as I say, it wasn't quite sort of as sophisticated as the other one in terms of its assembly, but they went really to town in terms of looking at the physics of the atmospheres. They looked up some data from Mars, from Venus, all sorts of stuff. So there's lots of ways, you know, if you manage to get to quality, because I mean both of those achieved all the kind of all the basic gold aspects of it, but they really sort of went for it in terms of extension. So that's why they got in the top 5. Both of them had a really nice kind of graphical user interface, so the way you can navigate through the data. But as I say, that's at the top end of things. You know, if you're not in that place at the moment, you know, you could please make a start with things like using spreadsheets to look at Kepler's laws. That will really help you with your studies. But I do encourage you to start thinking about some basic programming and how we can, you know, if you could pick a planet, plot me the orbit, and then you can refine that to be an elliptical orbit and work out the angle versus time. But there's a whole stage of things you can do. If the sort of integration part of it is a bit too much at this stage, then use the circular orbit model. You'll get something that looks a bit like this, but not quite as accurate. So there's plenty you could achieve. Okay, so there we are. I think what we'll do is we'll release all the 5 videos on the BPhO website, but you're going to get an idea of what they're like. Are there any more questions? Okay, so does the video have to be unlisted? Well, this is kind of up to you. If you want to broadcast your skills to the world, then be my guest. My personal view is that I think unlisted YouTube is quite a good idea. Obviously, if you, I think one of the students did have some music, so you know, music, if it's copyrighted, can't be listed. Otherwise, YouTube gets rather unhappy about that. How many submissions were there last year? How many got certificates? So I think we had about 45 or 42 submissions last year. Most of them were in pairs. So let's see if we can make that slightly more this year. That'd be great. Can you show us a video that won silver? Oh, I don't think I do at the moment, I'm afraid. So sorry about that. We don't have those available. But it will be not quite as good as what you've just seen. They probably won't have done any of the extension work. Right, I think that's pretty much it. So shall I stop sharing? Do you want to make any sort of further comments or any other questions that you have?
No, I think the main thing is that the information will be on the web page as soon as we can get our webmaster to give us access again. It's a slightly unfortunate circumstance. We can't do anything on the page at the moment, but these things happen. So that is your sort of go-to point for details, registering, copies of the videos, and so on. Okay, no, that's it. Thanks.
Yeah, so I think in the first instance, if you want to download the materials, go onto the Eclecticon page and you can get that access. And then in the next sort of few days or weeks, you'll have a formal sign up on the BPhO website, and everything will be there. Okay, just a few more. Is there an FAQ page? Well, hopefully the briefing document will answer all of those. So solo entries are fine. Yeah, I think we don't think we had any in the top 4, did we? Did we have any in the top 5 that were solo ones? Can't remember now. Certainly in the top 10 we did. Yeah.
I think Maddie Bailey was did it on her own, didn't she?
Oh yeah. So one of the top 5. So yeah, as I say, it you know, it just might be a bit more fun to work in pairs, particularly if you have a friend to work with. You might have complementary skills. But you know, it doesn't matter. How many students will receive gold? Well, that depends on how good quality the results are. It's you know, we don't have a fixed distribution, so you know, if you've achieved a gold standard, you'll get a gold certificate. Well, I don't think, so the course will finish from me now, so there'll be plenty of videos available, so hopefully information will be sufficient for your needs. Obviously, if you do find as many typos in the briefing document, I'm slightly thinking there might be a factor of 1/2 on the timing calculation there. Then perhaps you can send me a little email. We did spot something last year. So deadline, it's going to be early August, something like that. I think to be determined, but let's just say sort of first couple of weeks in August. If you do it, so you've got this term to do things, and also after the end of term as well. So if you're doing examinations and that kind of stuff, obviously they're really important. And then you can have a crack at the computational physics challenge in the first few weeks of your holidays. That would be great. Okay, who should we contact? So I think basically download the information, try and see if you can make sense of it. Once the sort of sign up is there on the BPhO website, which will be in the next couple of days, hopefully that should be self-explanatory. Obviously, if something doesn't work for you, then you can email BPhO, but in the first instance, to try and make sense of the material yourself. It should be fairly self-explanatory. There will be a video soon as well. This talk and maybe a slightly shorter one that I'll make. Okay. I think that's it. Good luck, everybody. Please give it a go. Right, do you want to sort of sign off, Robin?
Yep, I think they're leaving. So
I think you're meeting.
yeah, I hadn't realised I couldn't get onto the website tonight, so that's a bit of a pain. It's happened once before recently, so I'll get back there and I'll load all this stuff up.
Brilliant. Right, well, in that case, thank you everybody for attending the course, and if you're new, welcome to the BPhO Computational Challenge. Give it a go. I think the students who participated last year, really went on. There was a real benefit. There's some amazing things they produced, across the levels, from bronze all the way up to sort of the extension gold. So this is a good thing. This is a project for particularly if you're in the lower 6th or even earlier. Having a project for the summer that you're doing yourself that's not related to exams is a good thing to do. It's much more like what you'll do when you graduate. All right, so let's use this as an opportunity to learn some skills and have some fun. Okay, thank you very much, and we'll look forward to see your entries.
Excellent. Right, thank you very much. So I think we'll leave it at that. We'll fix things up. The website's on its knees at the moment. It's just out of date.
Right, good stuff.
Hey, I'm going to end the webinar unless you've got any follow on.
I don't think there's any more questions.
No, we're fine, thanks.
Thank you, Anna and Nina. Andy, talk to you soon at some point.
Indeed. Well, I will see you at the Royal Society next week.
Yes, yes. Okay, bye-bye.
All right, take care. Goodbye. I'm gonna
Thanks,
leave now.
Lena.
Thank you.